그래도 또 그런데 화면이 바뀌는데. 됐네요. Okay. Yeah. Today we're gonna start the chapter 5, norms for vectors and matrices. Okay. Okay. The Euclidean norm was a useful way to measure the size of real vectors. Then, is there any other measure? Is there any other tool to measure the size of vectors or matrices? Okay. Norm is going to be one answer for that. Why we have to study norm? Okay, let's think about a function 1 over 1 minus x. Okay. This can be written in this way for all x in C. But we need the radius of convergence to have this equality. We need a convergence. Okay, then, what about this? What if this? Can we write the same thing? Can we just replace x with a? On the equality that we had? It's not true. It's not always true. It is true when we have a condition like this. Answer is this. If we have a matrix norm that the norm of A is less than 1, then this is valid, like what we had for reals. And this, e to the x, we know what it is. Then what about e to the a? Can we use the same polynomial expansion like we had for e to the x? The answer is yes. It is valid for all well-defined matrix norm. Okay? Like what we had for reals. We had a radius of convergence as a condition to guarantee this equality. We had a counterpart of the radius of convergence of real for the matrix. That's the matrix norm. Okay, suppose f is a real valued differential function of a real variable, and if we know the value of f of x naught, then we can find this difference. Can be almost same as f prime of x naught. Okay. Here, what? When we try to find the inverse of A, suppose A can be written as A naught plus matrix E, which is the error part of it. Then instead of just inverse of A naught, finding the inverse of A naught plus the E, which is same as the inverse, then we can have the same effect. But in order to proceed, we should know the difference between this and this. This and this. Then what will be the relative error and what's the disparity between these two. Okay. The matrix norm will give answer for the difference of these two. Okay. Now we start the chapter 5.1 with the vector norm and inner product. Yeah, you have learned the definition of vector norms already. Okay, I will review that. Let V be a vector space over a field F. A function, this function is called the vector norm if it satisfies these four conditions. The first condition is positive semi-definiteness. The norm for all x, all vector, any vector, norm of any vector is non-negative. If the norm is equal to 0, if and only if the vector should be 0, it's called the positivity property. And the norm of scalar multiple of x is same as the absolute value of the scalar times the norm of x for all scalar c in F. This property is called homogeneous. And the last, triangle inequality. If this function satisfies these four conditions, we call that is a vector norm on the vectors. If it only satisfies these three conditions, 1, 2, 3, if this function satisfies only these three conditions, then we call it a vector semi-norm. Let's see. Suppose this function is a vector semi-norm, then we can have this inequality. It is very easy because y can be written as x plus y minus x. Then from the triangle inequality, we can write in this way. Okay, then we can move this one back to this. That give us 1. And also x can be written as y plus x minus y, and adopt this triangle inequality because it was a semi-norm. So we can move this one back to here. That gives us this. So if we have a vector semi-norm, that's always hold. Next, inner product. A function, this is called inner product if it satisfies these 5 properties. First, positive semi-definite, and positive, and is distributive on the right additions, and the scalar multiple of the first component can come out. This is called the homogeneous property. And also, x, the inner product of xy is same as inner product of yx. It is called the Hermitian property. If we satisfy these 5 properties, then this function is called inner product. Let's see. Suppose you have an inner product. Then the inner product of x and cy is same as here we can show these two are same, okay, because this is same as this, and we can, since because of the homogeneous property, C can come out. C can come out without the C on the first component can come out without any change, because this conjugate, we can write it separately like this, and this can be written as this. That's the property that we had. Okay. And also for this, we can have, we can split it. Yeah. Okay. We can also, if it's an inner product, we can also have the distributive property on the second component as well. Suppose we have a linear combination of vectors. These are vectors. Then this first component come out, and the second component come out. The scalars on the second component come out with the conjugate. So this can be written in this way. This is just this can be done one at a time, or you can show it by mass induction as well. And these are the properties. So, and also, if this is true for all y, if x and y, the inner product of x and y is 0 for all y in V, then means x should be a 0 vector. Okay, so it's easy to show. Yeah. But so let x is equal to y equal to x, then, and x inner product of x and x is equal to 0. That gives us x equal to 0 because of the positivity property. The other direction, if x is equal to 0, then this gotta be 0. This is the same, and this can be written in this way because of the distributive law, and these two are same, so we should have a 0 vector. Okay. So, and this works for all y's. So we have the left-hand side. And fine, those are the properties of inner product that you have already seen from the elementary linear algebra. And also, if we have this form, then that come out in this way, and this is complex conjugate, so we can have the square of it, something like that. So we have defined the vector norm and inner product. We are heading for the inner product space. Before we do so, we have the Cauchy-Schwarz inequality. Yeah, I will Cauchy-Schwarz inequality. Okay, here. This is the famous Cauchy-Schwarz inequality and triangle inequality for arbitrary vectors in an inner product space V. Okay. Suppose this is an inner product, then it satisfies this. Okay, here U is this vector and V is this vector, then the inner product satisfies this. We have two cases. If U is a 0 vector, then it's trivial. Equality hold. If U is not a 0 vector, then let U is not a 0 vector, then let this be P and that this be W. Let's say P be a projection of V on U. Projection, so it's perpendicular. Then what? P plus W is V. Okay, so W is V minus P. So this gone. W is V minus P. Then projection is this, as you see from the graph there. And the important thing is this W and P is orthogonal. So inner product is equal to 0. Then we have learned that P can be written in this way. P is equal to TU, and we have shown this T can be obtained in this way. This is from the first section of the elementary linear algebra book that you have learned. Okay, we know now we have everything. Because of the positive semi-definite property of the inner product, we have this. W can be written as V minus P. So, with the properties of inner product, we can split it in this way. Then, this is 0 because they are orthogonal. So, we have this. Now, W is equal to V minus P, so we can split it into this way. And P is equal to this. P is equal to this. We just replace it there. Then we have, this is called TU. So T can come out, and this is a square of the norm. And T come out, and T is same as this. T same as this. That is greater than or equal to 0. So we move this one to the other direction, and multiply the U, the norm of U square of U, norm of U on both sides. That gives us this. Because of the property of inner product, this is same as this. That gives us Cauchy-Schwarz inequality. Okay? So this is what you have seen it, and this is satisfies not only for the real vectors, it also works for the compressed vectors, and also it works for the arbitrary vectors in the inner product space. Okay. And the one thing that you haven't seen it before was this. You have to show this Cauchy-Schwarz inequality is sharp. Okay. And it's the equality satisfies if and only if one is the scalar multiple of the others. Here, the U is equal to X, just Y is equal to be the same from the above. Same thing. Yeah. Anyway, suppose you have X here and Y here, then it's the same thing. Okay. If one of them are 0, then it is trivial. If one of them are 0, then it's a scalar multiple definitely, and the equality holds. So all we have to think about is both of two vectors are non-zero vectors. They are not 0 vectors. Then one direction and the other direction here. First, if the square of absolute value of modulus of the inner product of X and Y can be written in this way, and we have this. Okay, suppose equality hold, that means this. That means this. But because of the property of norm, the W should be 0 by the positivity property of the inner product. What this means is this is 0. W is X minus P. P is T times Y. Here I think it's a Y here and X here. It doesn't matter. Doesn't matter. We can do the same thing on X and Y. Okay, anyway, so this is 0, so X this x can be written in this way, and x, that means x is a constant multiple of y. Okay? It's done. Suppose x is a constant multiple of y, then this can be written in this way. And we can rewrite it in this way. And C and C conjugate came out this way. This is same as this. This C can go in this way, and this C goes to go in this way. What that means is Cy is equal to x, and y is here. So we should have the equality. So Cauchy-Schwarz in Cauchy-Schwarz inequality, the equality hold means those two vectors are linearly dependent, just a scalar multiple of other. Okay. Usually this is the example, the exercise problem for after the Cauchy-Schwarz inequality. Okay. And if this is an inner product on the vector space V, then this function satisfies the properties of vector norm. Okay. You can easily check it. Okay. We call this vector norm is an induced vector norm by the inner product. From the inner product, we can make a vector norm in this way. Okay? Okay, that's the end of section 5.1. Here are some problem lists for you. In section 5.1, number 2 and number 10 is for Songtae, number 4 for Hana, number 6 for Horror, number 8 for the Ch5. Okay? Horror, what's yours? What is your problem? What? Number 6. Okay. Okay. Next. Yeah. The vector norms actually you have learned already, so we can go a little fast. Examples of vector norm. Section 5.2. This norm that you are very familiar with. This is called Euclidean norm, or Frobenius norm, or Schur norm, or L2 norm on Fn. Okay? And this sum norm, that is also called L1 norm, is defined in this way. Summation of xi's, absolute value of xi's. L infinity norm, also called the max norm, is defined in this way. Okay, this is what I have shown already. I showed you one norm, two norm, and infinity norm. Okay? Okay, and also LP norm is this. It's in between. Yeah, it's 1 to infinity. Okay? Geometrical. Okay, so yeah, now we have the example of vector norms. All of the above satisfies the 4 properties of vector norms. And also, we make a note that this LP norm converges to the infinity norm if we send P to infinity. And this is called the Minkowski inequality. This triangle inequality holds for any P bigger than or equal to 1. Okay, so triangle inequality that you have seen is valid for any P norm Okay? And Tikhonov theorem says this. You have learned from the Lie analysis class. Actually, this theorem is in the textbook of Lloyden, Lie analysis, page 234. Any finite dimensional, let's say it's n-dimensional, n-dimensional vector space V is over F. Any n-dimensional vector space V over F is isomorphic to Fn. Okay, this is what you have learned. Actually, this is the last theorem in chapter 9 of elementary linear algebra book that we are using for the freshmen at my school. Okay, anyway, this is the same theorem. Okay, since any finite dimensional vector space V over n-dimensional vector space V over F is topologically isomorphic to Fn, so the above can be used to induce a norm on V. I will show it. Okay. Let's see of AV are the set of continuous functions on AV. Then, for the function f in that set, we can define these functions as this. For the continuous function, now it's a continuous function. Okay. Before it was a vectors. Now we have a continuous function. We define in this way. This is called big LP norm and big L infinity norm. So the continuous functions. Okay, we had LP norms, little LP norms up there for the vectors. Now we have capital LP norms for the continuous functions. Okay, those are all satisfying the four properties of norms. Since this set of continuous functions is a vector space, so this function f and g's are all a set in a vector, a vector in a vector space. Okay. This is a way of writing. On those. Okay. First. For a Hermitian matrix, we define that matrix is positive definite if all eigenvalues are positive. Okay. We call A is positive semi-definite if all eigenvalues are non-negative. Okay, positive semi-definite. We call it is positive. We call it is positive definite if lambda is strictly greater than 0. 지우개. Okay, so also you have learned what is positive semi-definite and positive definite from the textbook for the elementary linear algebra. Okay. The Hermitian matrix is called positive definite if all of its eigenvalues are positive. Okay. A Hermitian matrix A is positive definite if and only if X star AX is positive for all non-zero vector X. Okay? Mn of C. Hermitian matrix is positive definite. Okay. Here is the proof. Since it's a Hermitian matrix, it is unitary diagonalized. So there exists a unitary matrix U and diagonal matrix D. with all main diagonal entries are eigenvalues of A. Let X is a normalized vector, and use those vectors to calculate X star AX. Then A can be written as U star DU. Okay? And this X star U star can be written in this way. Star of UX. And this is a scalars, and these are the vectors. So this just become this summation of lambda i's and the rows and the inner product of those two vectors. Important thing is here. The norm, the inner product of those two vectors can be written in this way, but U was a unitary matrix. So this is going to be 1. So this can be written in this way. So all of these are 1, but that means the lambda i's are all positive. This is true for each i's. So actually here all we have to do is A is a Hermitian positive definite. This can be, we all we have to show is this is non-negative, and we show this, we have this, but this is 1. So summation of positive eigenvalues are always strictly positive. That's what we have here. Done. Next, suppose this is true, and we show all eigenvalues of A are positive. Let's see. X star AX is positive, and say lambda is an eigenvalue of A. Then there exists an eigenvector of A corresponds to lambda. So, and multiply Y star on both sides, and divide by Y star Y, like this. But what is this? This is just, from here, this is just lambda. But that means is lambda is positive. Is from this condition. This is always positive on the given condition. So for the arbitrary eigenvalue of lambda, we have shown the lambda is positive from the given condition. That means all eigenvalues are positive. So that Hermitian matrix is positive definite. Okay? So this is a very important property. If you have a positive definite, then you can always say X star AX is strictly greater than 0. Actually, the set of this will take an important role in the study of matrices and numerical linear algebra. Actually, this set is called the field of value on A. We will see later. Okay, anyway, if F is a positive definite matrix, positive definite, then we may define an inner product of X and Y in this form, X star AY, or Y star AX. This is more popular. Okay, but anyway, we defined in this way. If A is positive definite, we can show this function satisfies the properties of inner product, 5 properties. let's see. X is this. This is true because it's positive definite. This is same as this, but this is 0. What that means? This means 0 when only if x is equal to 0. So this it satisfies the positive definiteness. Okay. Positiveness, positivity. Okay, next. This can be written in this way from the definition. This can be written in this way. This can be split in this way, can be written in this way. So it satisfies the homogeneity. This is the word distributive law. And this is defined in this way. The case can be written that way and in this way. So actually, yeah, this is different. Here, you know what's the difference? Yeah, here you have Cx here. The definition that we have, then when C come out, then C should be just Cxy. The reason that we have a C conjugate is we have to define this way. So just if we want to use the previous definition, then this should go as Yx in this way. Then everything works same. And here we won't have this. Okay. And third property, homogeneity, hold. And next, Hermitian property. Think about xy and yx. These two are one by one matrices, just a scalar. So the conjugate of scalar can be written as same as this. So we can have the last property, Hermitian property. So it satisfies all 5 properties. So it's going to be an inner product. So as you see here, if you define Cx is equal to C in this way, then you need you use this property. This is easier way, so that's why I use this. But if you define a norm in this way, or xcy is equal to xc like this, without conjugate, then if you choose this condition instead of this, then you can have this as an inner product. Okay? So this is it does work together. Doesn't matter. Okay. Anyway, you define this way. It's going to be in your inner product. Okay, so positive definite give us an inner product without any difficulty. The matrix A and matrix B is called isometry for the vector norm if the vector norms are same. I think we have seen it already. If this is true for all vector x, then it is isometry. Isometry. Metric, distance is same. Distance doesn't change when you multiply the matrix B on that norm. Okay, so that's the definition. Okay, you have seen those for the unitary matrices already in chapter 2. Here, you can try some exercises. And here's a problem for section 5.2, page 267. Jin, Hana, and Horol, you may try just these 3 problems. Okay, Hana? You want to try this one. And the others will see what the others do. Next, section 5.3 and 5.4 and 5.5 deals with the algebraic and analytic and geometric properties of vector norms. Usually you learn this from the functional analysis class. So we don't have to recover those sections, but I will give a brief description on what is in. Actually, in the first edition of this book, matrix analysis book, and we found out something's wrong on the theorem 5.3.1, so we pointed out and it was replaced. That's why, Professor Leroy Beasley's name is there. Because I was a student to point out that first theorem. So now, your new version has a proper new theorem instead of the old one. Okay, anyway, if this is a norm on Rn, and x and y hold this inequality component-wise, but still, the norm may not keep the order. See the example. Let's define a norm in this way. Then A is positive definite. If you deal with the scalar, the layers, then the conjugate doesn't make any change. So whatever you choose, it doesn't make any change. It's all one by one scalars, and conjugate doesn't mean anything. So it's always, it works. So for the real, it is an inner product. This matrix is positive definite. We know this is an induced vector norm, as you see, and let x and y be in this way. Okay. Then component-wise, it satisfies this inequality. You find the norm of x, which is 3/2, and norm of y is equal to 1. As you see, the order has been changed. Okay? So, in general, this component-wise inequality is not invariant on norms. Okay, this is a basic knowledge before we start the new subject, matrix norm. You have learned vector norms already, and this will serve for the review of vector norms that you have learned. Now, we're going to start the matrix norm that you have not studied before. Any questions on matrix norm? On vector norms? 성태? Any?